So now we're going to get into talking about acceleration analysis, and we're going to start with normal and tangential acceleration, and we'll move on to Coriolis and sliding acceleration after that. So with this will allow you to really do an acceleration analysis of any linkage that has rigid links, but as you move to as you have sliders that are rotating, that's when you need to talk about Coriolis and sliding acceleration. So let's start off with kind of expanding where we were with velocity analysis. So one thing I need to mention first is that to do an acceleration analysis, you do have to complete a velocity analysis first, and then you have enough information so that you can do your acceleration analysis. So if I have some arbitrary link, joints A and joints B, it has some angular velocity, omega 2, and some angular acceleration, alpha 2. I can then say, well, let me start off by describing its velocity. So I would have velocity of point B, and I could have a vector equation that's saying that's equal to the velocity of A plus the velocity of B with respect to A. And I would know how to draw those. And again, if this was a pinned mechanism, where A and B are connected off as input and output links, I could then draw all that and I could solve for them, and we've done that in a couple of different ways. Now, when I go to acceleration analysis, I simply am now going to say, I've got the same idea of a vector equation of the acceleration of B is equal to the acceleration of point A plus the acceleration of B with respect to A. But one difference now is that acceleration of B with respect to A has at least two components, and up to four. So the two components in this case are that we have one piece of it that's pointing back towards A. So this would be our acceleration of B with respect to A, and we call this the normal component. So sometimes we have the n down here, and I'll stick it up top just because, well, I'll keep the same nomenclature that the book is using. So an n means it's normal acceleration, and this is also what we sometimes refer to as centripetal acceleration. So it's the piece that's pulling you back towards the center of rotation. The second piece that we have, if we have angular acceleration, is a component that's perpendicular to that. So this would be the acceleration of B with respect to A tangential. So those would then be the two components that you have for a rigid link. So recognize that I need to break down this acceleration of B with respect to A into two components here, which are the normal component and the tangential component. And so if I express these, the expression for B with respect to A normal is going to be equal to, and I'll leave the vector hat off for now, is going to be equal to, in just magnitude, omega squared times RBA. So the radius vector 2B from A. So this is saying omega squared times R. That's our centripetal acceleration. We've seen that many times in physics. And one thing to pay attention to is that this is pointing inwards, or the opposite direction of RB. And when we approach this analytically later, we'll see where that comes from in terms of the math. But for now, just realize this points inward, or opposite RB. RBA. All right. And then the second component, our tangential component, acceleration of B with respect to A tangential, this is then just equal to the angular acceleration alpha times the radius vector RBA. And this is always going to be perpendicular to the radius vector RBA, and it's going to be in the direction of alpha. So perpendicular to RBA in the direction of alpha. So really not too bad. It's one step more than doing our velocity analysis, where we only had that one component of it that is perpendicular to the radius vector. Now we have two components, a centripetal component and a tangential component. So now let's apply this to a problem that is kind of an intro 4-bar problem. And this would be a crank slider that looks very similar to an internal combustion engine, where my link from A to B would be the crankshaft. My connecting rod from B to C would be the coupling link, and then C, that block there with what's connected at joint C, that would be the slider block, or the piston. So we're going to start off by saying, remember, I needed to do a velocity analysis of this first. And so I've done a graphical velocity analysis that's completely contained in the upper right there. And so what I would have written is that the velocity of point C is equal to the velocity of point B plus the velocity of C with respect to B. And then you can see I solve for that by, first of all, getting to the velocity of B, which would be coming from omega of that input link. So I'm given that my input link has a angular velocity of 94 radians per second, and that's constant, which means that alpha, in that case, what's that? Alpha, what link? Alpha 2 is equal to 0. So that's what constant means. And then from that, I could then calculate the velocity. So if I got the velocity of B, then I know the direction of the slider velocity, VC, is going to be along the axis of the slide. And then C with respect to B is perpendicular to that link BC. So that then gets me to this point right here, and then I can measure off the velocity of C and the velocity of C with respect to B. And one of the reasons I want to do that is because I'm going to need the angular velocity of link 3, the coupling link, and I get that from the measured velocity of C with respect to B divided by the distance from B to C. So that's all the velocity analysis that we've done previously. So now let's take this to the next step of doing our acceleration analysis. So I'm going to start off by really doing the same thing, but doing it now for acceleration, where I'm going to write my equation, and my acceleration equation will be the acceleration of C is then equal to, and I'm going to break this into components right away, so I'll leave the vector hats off. So the acceleration of C is equal to the acceleration of B, and this will have both normal and tangential components. So I'll have the two different components of it, so the centripetal and the tangential. And then I will look at the acceleration of C with respect to B, both the normal and the tangential components of that. So that is now my acceleration equation. And I look at this and I say, which one of these do I know in terms of direction and magnitude? And to be more proper, I should, let me leave my vector hats on this because this would be more proper. As I look at this, I would then say, which one of these do I know in terms of directions and magnitudes? So the acceleration of C, this is the slider block moving along its axis of slide, or the piston. So this I will know its direction because it's sliding. I do not yet know its magnitude, so I'll leave that as a question mark. That's one thing I'm trying to solve for. What's the acceleration of that piston? And then I look at B. Well, remember, B is on this link 2 that I happen to know its angular velocity, and I know its angular acceleration is 0 in this case. So the normal component, which is going to be pointing back towards the origin, so this will be pointing right back down there, that will be the acceleration of B normal. I'll know its direction, and I'm also going to know its magnitude, because the magnitude of acceleration of B normal will be equal to omega 2 squared times the distance from A to B. And so as I measure this out, I've got a distance of 2 inches. I've got an angular velocity of 94 radians per second. So I multiply those out and I get 17,766 inches per second squared. So that's my acceleration of B. I know its magnitude. Now, the acceleration of B tangential, the direction of that would then be perpendicular. So it would be in that direction or perhaps this direction based on which way alpha is. So it would be this piece right here. That's the acceleration of B tangential. And its magnitude is going to be based on alpha 2. And part of the problem statement tells me that alpha 2 is equal to 0. So I say, yes, I know the magnitude is equal to 0 because alpha 2 is equal to 0. So that simplifies this problem, but if it did have angular acceleration, we would just have that as an extra component, which is a known in this case. So then moving on, I would have the acceleration of C with respect to B, normal. So this I will have direction. And remember, this is going to be pointing back down this, this link right here. So this will be acceleration of C with respect to B, normal. So I know its direction is pointing back down. And its magnitude is going to be equal to the angular velocity of link 3, that coupling link, or the conrod, squared times the distance from B to C. So I will also know its magnitude. So I'll just write it out right now. The acceleration of C with respect to B, normal, is equal to omega 3 squared times the distance from B to C. So remember, omega 3 was calculated from the velocity analysis. So that was at 24 radians per second. I'm going to multiply it by the distance from B to C, which is 6. And so as I multiply these out, I end up with 3,504 inches per second squared. So now I know the normal acceleration of C with respect to B. The last component here is the tangential component of C with respect to B. And this will be then perpendicular. So it'll be either heading that way or heading this way, depending on the alpha of that link. So I know its direction, either this way or this way, but I do not yet know its magnitude. So I'm trying to solve for that. So now I've got this vector equation. I've got, and again, remember a vector equation is equivalent to two scalars, and I've got two unknowns, which are the magnitude of the acceleration of C and the magnitude of C with respect to B tangential. So now I'll use the same method we did using graphical velocity analysis to solve this acceleration problem. So I'm going to start off with this origin of A right here. And you'll see that I've set up a scale that will help me sketch this. So I've said 1 inch of length is equal to 5,000 inches per second squared. So let me just grab a different color here. So I will quickly convert these. So if I've got 17,766 inches per second, this ends up being 3.55 inches of distance. So just dividing that by my scale of 5,000, and again dividing the scale of 3,500 by 5,000, I end up with 0.7 inches. So those are my two scales that I'm going to stick on there. So again, I'm going to start off by drawing what I know the most about. So I'm going to start with the acceleration of B normal, and I will draw this at, let's see, this will be heading back down towards the origin. If I was in class, and what I'd recommend you do is take your two triangles, your two 45, 45, 90 triangles. You would set one of them up on A to B. You would then slide the other one along it until you can draw a line that is parallel to it from OA. So then this would be heading back towards A, and this magnitude here is going to be 3.55, something along those lines. So this will be the acceleration of B normal. And that's what I'm going to draw first. So this is supposed to be 3.55 inches. And again, back down towards A from B. All right, so then the next thing I'm going to add to this, the next piece is the acceleration of B tangential, which is 0. So that's really easy. It's done. The next piece is the acceleration of C with respect to B normal, and I know both its direction and magnitude. So its magnitude is going to be 0.7. It's going to be heading back down the connecting rod, so it's going to have something along these lines right here. This will be the acceleration of C with respect to B normal. All right. Now adding on to this, I've got another component here, which is C with respect to B tangential. I know its direction, but I don't know its magnitude. So this is going to be perpendicular to C with respect to B, so it's going to be somewhere along that. So this will then be the acceleration of C with respect to B tangential. So I know its direction, but not know its magnitude, so I drew it as a long line. And finally, I now have the acceleration of C, where I know the direction of it, which is vertically up and down along the axis of slide, but I don't know its magnitude, so I'm going to draw it vertically. I find its intersection right here. This would then be the acceleration of point C. This then also defines the acceleration of C with respect to B tangential. So now I've closed my velocity polygon, and I have a magnitude that I can measure off here, where this ends up being 2.4 inches, which is the equivalent of roughly 12,000 inches per second squared. So now I have solved for the acceleration of C using that. And so that's about 31 Gs of acceleration at the piston based on this given angular velocity. So kind of backtracking here and walking through our steps, we had to complete a full velocity analysis. And the reason we need that is because we need the angular velocities of the links that are rotating, because that's important for the centripetal acceleration, the normal component. We then wrote our acceleration equation, and I just jumped straight to having the normal and tangential components. But if you want to take an intermediate step and just say the acceleration of c is equal to the acceleration of b plus c with respect to b, and then break it into the components, that's fine as well. We then said, well, what components do I know direction and magnitude? For this case, we knew all the directions, and 2 magnitudes we did not know. We calculated the magnitudes that we did know. We set up our acceleration polygon, and we closed it with the 2 unknown magnitudes that intersected. So that allowed us to solve for the acceleration of c. So we'll continue doing this for these rigid joints, and then we're going to add 2 other forms of acceleration, Coriolis and sliding, as we get to a rotating sliding sort of situation.